Hi there, this is Ms. Cronin here. In this video, we are going to be learning about complex numbers and how to work with complex numbers. Where do they come from? What are they used for? And this corresponds with 2.5 and 2.9 in your textbook. Okay, so let's just start here. We've got an equation here, x squared plus 1 equals 0. Let's solve that for x. So we would start by subtracting 1, so I get x squared equals negative 1. And then when I take the square root of both sides, don't forget plus or minus, we get x is equal to plus or minus the square root of negative 1. All right, well, there's a negative underneath the square root, so this quadratic equation has no real solutions. So how do we handle that? We can find the solution if we use something called imaginary numbers, which are not really imaginary. Thought they were imaginary at first, but they're used in a lot of different places. So the imaginary unit is usually I. In electronics, I is already used for something else, so we'll look at that in a little bit. It's used for current, if you're familiar with electronics. But so they use a J in electronics, but most applications use the letter I, a lowercase I, and it is equal to the square root of negative 1. That's called the imaginary unit. And then if you're going to square, if you take I squared, that means we would square the square root, which cancels out. So I squared is equal to negative 1. And this is a big part of the basis of what we're going to need to know. All right, so we're going to use this imaginary unit to express each number here in terms of I. So we can split up the square root of 25, square root of negative 25 into the square root of 25 times the square root of negative 1. And then the square root of 25 is 5, and the square root of negative 1 is I. So the square root of negative 25 is 5i. All right, so then we have 4 times the square root of negative 16. Why don't you try to do this one? Pause it and come back. We have 4 times the square root of 16, which is 4. So 4 times 4 is 16, and then our square root of negative 1, again, is I. Simplifying the square root of negative 75, we're going to pick out perfect squares here. So what I'm going to do is I'm going to write 25 goes into 75, so I'm going to write this as 25 times the square root of negative 1 times the square root of 3, because 25 times 3 is 75, times negative 1 is negative 75. And I can take the square root of 25, it is 5, the square root of negative 1 is I, and then the square root of 3 will just leave under the square root because there are no more perfect squares underneath the radical. So 5i square root of 3 would be the simplified version of that. All right, so a complex number is a number that can be written in standard form as a plus bi. A and b are both real numbers, and I is equal to the square root of negative 1, just like before. Every complex number has a real part and an imaginary part. I should have mentioned this at the beginning. These notes are posted in Canvas. You should print those out and follow along with me because this is it's your notes, but it's also your assignment for these two sections. All right, so next we're going to classify numbers. So we have spent a lot of time working with real numbers throughout your life, but real numbers are actually a subset of the complex numbers. So this is like the big overarching set of numbers. Complex numbers, I'm just going to write that instead, can be broken into real and then imaginary numbers. So those are imaginary numbers, and real numbers are subsets of the complex numbers. So some complex numbers might look like 4 plus 2i. That's a complex number. because, well, it has a real part and an imaginary part. The number 6 is a complex number. All numbers are complex numbers, but then we can split them into real and then imaginary. So this first example is going to go under imaginary. The second example would be a real number. You can have negatives, you can have fractions, you can have irrational numbers like pi. The complex numbers encompass all the numbers that exist. Okay, so imaginary numbers are these guys that have these negatives underneath square roots. So square root of negative 16 is an imaginary number. 5i is an imaginary number. 7 minus 2i. Those are imaginary numbers when they have that I, that imaginary unit, as part of the number. All right, so real numbers include all your rational and irrational numbers. So irrational numbers, let's just break this down. We have irrational numbers and we have rational numbers. And then while we're at this, let's look at complex numbers are represented with a C, if you want to learn some shorthand with an extra line through it. Real numbers look like that. We have irrational and rational numbers. Irrational numbers can be represented with the letter F with an extra bar. It's not used as often as some of these others, but it can be used. And Q with an extra bar represents the rational numbers. All right, so the real numbers include both irrational and rational. So pi, which is going to also fit into irrational. Irrational numbers are numbers that never cannot be written as fractions. And they are numbers as decimal, in their decimal form, never end and never repeat. So pi, the square root of 5, the square root of 2, those are all irrational numbers. Rational numbers include like the number 5 is a rational number because it can be written as a fraction. The number 22 over 3, and we can throw negatives in there as well. So all positive and all negative, rational and irrational numbers. You can have a simple fraction like 1/4. You could have 0.3 repeating, which can be written as a fraction as 1/3. So, but again, I'm going to put a couple of more of these irrational numbers in there just so you realize that real encompasses both of the rational and irrational. All right, so let's go down to rational numbers. Rational numbers can be written as fractions. Fractions that involve integers. So like 1/3 is a fraction that involves integers, and we'll talk about what integers are in just a second. So this also means if something can be written as a fraction, it can be written as a terminating. Terminating means end, or repeating decimal. Any decimal that terminates or repeats can be written as a fraction, so those go hand in hand. Okay, so like if you had 0.2 repeating, that's rational. The number 4 is rational. The number -7 is rational. So it's a quotient of integers, another way to say that. All right, so those are some rational numbers, and let's go down here to the next subset, which is the integers. And integers can be abbreviated with a letter Z with an extra bar. Your integers are, so these dots mean it would keep going in the negative direction, but I'm just going to start with I'm just going to show a pattern. -3, -2, -1, 0, 1, 2, 3, ... means they keep going like that forever. So it's all of your whole numbers and all of your positive and negative whole numbers. So we can order the integers. We can't write the other subsets of numbers that we've covered already in order, because there's always something in between. So like in between 0 and 1, we have an infinite number of rational and irrational numbers. So the first subset that we can actually write in order are the integers. And the integers can be broken down a little further into whole numbers. The whole numbers are just the positive, starting with 0 and then going up. It does not include the negative numbers. So 0, 1, 2, 3. And then we have what's called the natural numbers, also called counting or natural numbers, starting with 1. So when we count, we start with 1, right? So natural numbers can be represented with the letter n with an extra bar. 1, 2, 3, 4, and so on up to infinity. Okay, so I'm gonna stop here with this video, and then we'll start part 2 in just a bit.